Alright, so in this next video, we're going to go over matrix equations. So this is going to be sort of a generalization of the sort of systems of linear equations that we've dealt with in earlier on in section 6.1. The reason we're looking at this is going to sort of develop the computational methods that we need for computing matrix inverses in section 6.3. Now, we know that if we have m equations in n variables, right, that means that A has to be an m by n matrix. We know that we can write this in matrix form. We can write it in this form: A times x equals B, right? So x here, remember that x is this column vector containing the variables. And we know that B, this guy B on the right hand side, right, this is going to be a column vector that contains the constants on the right hand side of our equation. And we know that generally when we do this, right, most of the time m doesn't necessarily have to equal n. We've seen lots of examples of systems where there were more variables than equations, and a few examples where there were more equations than variables. We know that both can happen. And so what we want to do now is we want to generalize a little bit. We want to consider now equations of this form: A times x equals B, where we don't restrict ourselves to the case where x and B consist of a single column. We want to allow them to have many columns, right? So if A is n by n, and I want to multiply by x and get something which is m by k, the rules of matrix multiplication dictate that this guy x here must be an n by k matrix. Okay. So we're gonna try to set this guy up, and so the idea here is going to be to say, well, if I let x be, so I'm going to take x and I'm going to divide it up into columns, right? Well, before we do it, let's just kind of see how this looks. So if I take x and I write it as x11 all the way across to x1k, x21 across to x2k, down to xn1, xnk, right? I can take this matrix and I chop it up into columns, right? So I write this as, let's simply call this first column the vector x1, right, all the way across to the vector x sub k, right? So instead of having a single column vector worth of variables, we now have k different column vectors worth of variables. Similarly, B, the matrix B, could be written as sort of a B1 all the way across to bk, right? And so one of the ways to think of this, and this is how we will think about it, is this is actually now, it's, before we had one system of m equations and n variables, what we get now is, well, it's k systems of m equations in n variables, right? So that sounds like an awful lot of work, right? Now, instead of having to solve a single system of equations, we're solving k systems of equations, right? It's not as bad as you might think, though, because notice that every single one of the systems has the same coefficient matrix. This matrix A is going to be the matrix of coefficients in each case, and we know that it's the matrix of coefficients that dictates what our row operations should be. And that means that for each one of these case systems, we're going to do the exact same series of row operations for every one of the systems. So we try to do this systematically, right? So the first thing to notice is once we've taken our matrix X and we've chopped it up into its columns, x1, x2, down to xk, well, because we do this row times column procedure when we do matrix multiplication, the first column of A times X is A times the first column of X, the second column is A times the second column, and so on, right? And we want that to be equal to, B, right? So we want that to be equal to B1, B2, down to BK. Right, so we want something that looks like that, right? And so you see now that you do indeed get. Here's my K systems. My K systems are going to be A times X1 equals B1 all the way down to A times XK equals BK, right? And the important thing to note is that the left-hand sides, aside from the way we're labeling the variables, the left-hand side is exactly the same for every one of the systems. The only thing that's different is the right-hand side, right? So in each case, it's going to be the same. It's the same left-hand side, different right-hand side for each one of them. Okay, and if you think about how you would go about solving each one of these systems, and now there's a bit of a cheat going on here, right? We don't necessarily get the solution vector here over at the over here on the right-hand side. When do I actually get that guy over there on the right-hand side? If you think to the examples that you've done before, this is what you get when A is square, so n by n, right? Because normally, if the number of variables is different from the number of equation, then the vector xk and the vector bk, those are not vectors of the same size unless A is a square matrix, and so that wouldn't even make sense, right? Because we know that those columns remain the same size as you do your row operations. And so if A is an n by n matrix, and if the solution is unique, right, we know that that's exactly what we get in the reducer echelon form, right? We know that the reducer echelon form, it's going to look like, right, this is going to look like, it's going to look like this. It's going to be 1, and then zeros, and then 0, 0, 1, 0, and so on, 0, 0, 1, right? These leading ones in each column, and then your constants are going to be, well, some A1, A2 down to AN, right? And so in this case where you're dealing with a square matrix and a unique solution, right, you get x1 equals A1, you get x2 equals A2, down all the way down to xn equals AN, right? And that's your solution, and that's the sense in which you would get that solution vector over there on the right. And now, as we mentioned, it's going to be this same row operations for every single one of these guys, right? For the first one, we do our row operations to get A down to this reducer echelon form, and we get this solution vector x1, right? And then for the next one, we do the same row operations, right? And whatever we do on the left, we also do on the right, and we get down to here. Well, rather than doing this a whole bunch of separate times, we just do it all at once. And so the way we solve is we take our matrix A slash B, and we try to get this thing down to the reducer echelon form, and then X on the other side. We try to tackle all of them at once, right? So here's how this kind of looks. Here's the setup for it, right? Here's the algorithm, right? We want to solve A times X equals B in the case where A is square, okay? But B could have any number of columns. The number of columns doesn't really matter here. So how do we solve it? We form this augmented matrix. We perform our row operations until we get down to the reduced row echelon form, right? And it's these guys, it's whatever is here on the left, to the left of the bar, that's going to tell us when we're in the reduced row echelon form. Now, if we are in this situation where the reducer echelon form is the identity, remember the identity is this matrix that has 1, 0 all the way across 0, 0, 1, right? it's exactly this matrix that you expect when you're in the case of a unique solution, right? Then the the matrix C on the right is going to be the solution that we're looking for. If you don't get the identity, that means you're going to get some, there's going to be some columns that are missing their leading ones. For in the case of a square matrix, that means you're dealing with rows of zeros. Well, when that happens, you're going to have to analyze each one of your columns separately and decide whether or not there's a solution. And the one thing to note here is that in this case, a solution means that you have a solution for all columns, right? So if B had, say, 3 columns and you were able to solve, if you were able to solve A times x1 equals b1, and that one worked out fine, and then you did A times x2 equals b2, and that one worked out fine, and then you did A times x3 equals b3, and you found that there was no solution for one of those 3, then there's just simply no solution for the whole thing. There's no matrix X that's going to work. All right, so in the next video, we'll do some examples to show you how this works.